Please tell me if you cannot hear me. Can you hear me? So, uh, right, so I would like to begin by thanking Tamara-san for the introduction, and also thanking the organizers for this wonderful opportunity to speak at this workshop. So it's very good to see many of my colleagues after so many years, and even in some cases after so many decades. So I would like to share the PDF file of the slides. So I hope that you can see this. So I would like to talk about Teichmu dilations of varying hues from complex Teichmu theory to IUT to GT. So this is joint work in progress with Tsujimura and also Tsujimura Saidi. And so I will not announce any precise results in this talk, and also Tsujimura will not announce such precise results in his closely related talk, because we're still in the process of writing the papers and checking all the details. And we hope that at least so that the joint work with Tsujimura, which consists of 2 papers, we hope that we will be able to make the papers public sometime this year, 2025. Of course, that's not a guarantee, but so unfortunately, we didn't quite finish writing up the papers before this workshop. So these slides are available on my website. So I would like to begin by discussing a ring theoretic interpretation of classical complex Teichmu theory. So to briefly review classical complex Teichmu theory, so more details can be found, well, not so many details, for instance, in this example 3.3.1 of this essential logical structure survey. So the most fundamental deformation of complex structure in classical Teichmu theory is given by deforming the complex structure in this way. So for lambda, a positive real number greater than 1, we map z. So this is the standard complex coordinate in the complex plane, which can be written as x plus I, y, where x and y are real numbers, to zeta, which, so this is c plus I eta. So we multiply the x coordinate by lambda. So in other words, we're deforming the x coordinate and keeping the y coordinate fixed. So this is a non-holomorphic map. And so this is the most fundamental deformation of a complex structure. Right, so the complex structure, the holomorphic structure relative to this coordinate z, is different from the holomorphic structure given by zeta, even though you can think of them as both being functions on the same underlying real analytic manifold. So more generally, on a Riemann surface, so if one starts with a single oriented topological surface S, so we can start with a holomorphic structure H1 on S and a square differential relative to this holomorphic structure, and then form the Teichmu dilation, or a Teichmu map, obtained by deforming, that is to say, in the fashion described above, the canonical holomorphic coordinate obtained by integrating the square root of the square differential along various paths on the surface, so as to obtain a new holomorphic structure. So this is the most classical definition of a Teichmu map. So if we write OHI, where I is equal to 1 or 2, for the sheaf of holomorphic functions on S relative to the holomorphic structure HI, and OR for the sheaf of complex valued real analytic functions on S, then, so first of all, we note that for connected open sets U in S. ORU is a domain, unlike the case with continuous or smooth functions. So there's to say, in some sense, so we can even think of real analytic functions as holomorphic functions defined on some germ, some indefinite open neighborhood of the diagonal inside the product of the Riemann surface with its conjugate Riemann surface. So anyway, it's in some sense very close to being like the holomorphic sheaf of holomorphic functions, but it's not exactly the sheaf of holomorphic functions. And so the point here is that one can interpret these Teichmu maps of classical Teichmu theory as being allowing one to obtain these embeddings of OH1 and OH2 into OR. So we can simultaneously think of OH1 and OH2 as subrings of so sheaves of subrings of OR. And so if one looks at the sections over a single open connected open set, they're subrings inside a domain. So it's a natural embedding inside the same domain. So this is the picture that we want to have in mind when we look at the other versions of Teichmu theory, so which will be more arithmetic. But the point is that this picture is essentially the same picture for all of these versions of Teichmu theory. So we would like to consider various arithmetic analogs of this function theory. So in the second section, I would like to briefly review interuniversal Teichmu theory. So this talk is not intended to be a detailed exposition of IUT. So now there are various survey texts, this alien survey and the essential logical structure survey on IUT, as well as many, so I don't know whether it's over 100, but many tens of videos and slides, which are available. So the 2021 workshop, 2021 workshops on IUT, the videos and slides are available at these URLs. Although you need to get permission from one of the organizers to access the videos. And also, I recently I've given a series of lectures, the Duango lectures on IUT, which again the URLs are available. So they're YouTube URLs at request. So right, so the main idea, again, I don't want to give a detailed explanation of all aspects of IUT, or I certainly don't have the time to do this, but I want to explain the main idea, and that is the following. So one starts with an integral domain R, such as, for instance, the ring Z of rational integers, equipped with the action of a group G, and an integer, positive integer greater than or equal to 2. And so for simplicity, we assume that the element corresponding to this integer n is non-zero in R, and that R has no non-trivial nth roots of unity. So this is not an essential assumption, but just for simplicity. And we denote by this R triangle the multiplicative monoid given by the complement of 0 in R. And then we observe that the nth power map on our triangle determines an isomorphism of multiplicative monoids equipped with actions by R. So this is the map of the isomorphism of multiplicative monoids given by raising to the nth power. And so it's equivariant with respect to these actions by G. but it does not arise from ring homomorphism, so it's clearly not compatible with addition. So this is because of our assumption on N. We're not in characteristic P. So where P divides N. Next we want to consider two distinct copies of this integral domain R, equipped with respective actions by two distinct copies of G, which are denoted by a single and double dagger. So we use similar notation for objects with labels given by this dagger and double dagger to the previously introduced notation. And so then one might use the isomorphism of multiplicative monoids arising from the nth power map discussed above to glue together this monoid arising from one copy of R and G to this monoid arising from the other copy. And so here the notion of the gluing may be understood at a naive level, just as a quotient set via identifications, or closer to what is actually done in IUT as an abstract diagram. So this is the point of view of graphs of groups, or even closer, graphs of n-abelioids, essentially graphs of Galois categories. And so we can glue the ring, one copy of the ring R to the other copy of the ring R along this multiplicative monoid. And so this gluing is compatible with the respective actions of G relative to the isomorphism given by forgetting the labels. But this is an important and fundamental aspect of IUT, which I'm sorry. So, which is often misunderstood, and that is that since the nth power map is not compatible with addition, this isomorphism may be regarded either as an isomorphism of abstract groups, or as an isomorphism of groups equipped with actions on certain multiplicative monoids, but not as an isomorphism of Galois groups. So in other words, an isomorphism of groups equipped with actions on rings or fields. So the point here is that the only structure that's preserved, so the additive structure of the ring is not preserved. It's only the multiplicative structure that is preserved. And so this gluing isomorphism can be thought of as an isomorphism that is compatible with an isomorphism of abstract groups, or as an isomorphism of groups equipped with actions on multiple monoids, but not as an isomorphism of groups equipped with actions on rings or fields. And so this is in some sense the starting point of the notion of interuniversality. And here, so the universe refers to Grothendieck universes of the sort that occur when one considers topoi such as Galois categories. And the nature of the indeterminacies that arise here, that from the fact that one can only consider these copies of G as abstract groups, is entirely at a foundational level, qualitatively, similar to the indeterminacies, the inner automorphism indeterminacies of SGA1. But the only difference is not foundational, but rather the difference arises from the fact that whereas in SGA1, the ring structure is always preserved. One always considers morphisms of rings or schemes. Here, one only has the multiplicative monoid structure. So then one wants to consider the problem of describing certain portions of the ring structure of the left-hand copy of of R in terms of the ring structure of the right-hand copy of R in a fashion that's compatible with the gluing and via a single algorithm that may be applied to the common. So this is a logical AND operator. Glued data to reconstruct simultaneously certain portions of the ring structures of both sides. So one wants to simultaneously reconstruct the ring structures of both sides, or portions of the ring structures of both sides, by the single algorithm, up to suitable relatively mild indeterminacies. So this is in some sense analogous to the theory of crystals. And so this problem at first glance, or in general, a priori seems hopelessly intractable. So if one thinks of the case of Z, one wants to have a single algorithm, for instance, for reconstructing the additive structure of Z just from the underlying multiplicative monoid of Z, that simultaneously recovers both the additive structure before you raise to the nth power and the additive structure after you raise to the nth power. So, and you might allow for mild indeterminacies, but still this seems like an intractable problem. And so one important point here is that it's important to distinguish these two copies of G that appear because one wants to decompose this diagram, this gluing diagram, into pieces. So one has, for instance, the common glued together portion, and then the portion on the left-hand side, the portion on the right-hand side. And one wants to consider, for instance, symmetry properties that allow you to interchange the left and right-hand sides. And this can only be done by decomposing this diagram into pieces. And so if you don't decompose into pieces, it looks as though you can just always think of G as one rigid copy of G. But once you decompose the diagram into independent pieces, so for instance, one independent piece is this this common glued together portion where you no longer have a ring structure, you just have an abstract monoid structure. And so the point is that, right, so one wants to consider symmetry properties, and this can only be done by decomposition, and so into pieces, and so then you need to think of the two copies of G as being distinct. So one well-known elementary example of this kind of situation is the case where n equals p, and so one is considering p-adic rings. So working modulo p, so this working modulo p can be thought of as a sort of indeterminacy. This is the analogy with crystals. So modulo p, there is a common ring structure that is compatible with the p-th power map. But what's remarkable about crystals is that they allow you to work with, for instance, vector bundles over p-adic rings, even just by using this this modulo p portion. And so this is one sort of non-trivial instance of this kind of situation. So another important example, which is in fact the motivated example that gave rise to IUT in some sense, is Falting's proof of invariance of the height of elliptic curves under isogeny, where one, so it's a special case of this Falting's proof, under the assumption of the existence of a global multiplicative subspace. So this is a very special case of Falting's proof. And so this is discussed in detail, for instance, in this essential logical structure survey, example 3.2.1. And so in some sense, one can think of IUT as a theory designed to generalize this kind of argument to the case of arbitrary elliptic curves, where you don't necessarily assume the existence of a global multiplicative subspace. So at any rate, this is what one would like to do. This kind of algorithm is what one would like to achieve, and this is in fact achieved in IUT by means of the multi-radial representation for the theta pilot via Abelian geometry. So again, this is because one has to work with these abstract groups. So one wants to see to what extent one can recover, for instance, various ring structures from these abstract groups, and also the p-adic and complex logarithm and theta functions, and Kummer theory, which allows one to relate Frobenius-like and étale-like versions of objects. So the Frobenius-like versions are the versions that correspond, to, for instance, to these rings and monoids here, whereas the étale-like versions are the versions that arise from Abelian reconstructions applied to these abstract groups. So the main point is that, again, the multiplicative monoid and abstract group structures, but not the ring structures, are common. So this is the logical AND operator to both sides, and can be used as input data for an algorithm to reconstruct the multi-radial representation for the theta pilot, which is a common container for certain portions of the ring structures, of these distinct ring structures, which I refer to as arithmetic holomorphic structures. So again, the point is that we get a similar kind of diagram to the diagram in section 1 with complex, in the case of complex Teichmu theory. So we embed the ring structures from both sides into some common container. And so when R equals Z, or more generally the ring of integers of a number field, one can think in terms of the height or a log volume for some x. So for instance, a non-zero integer, the height is, roughly speaking, the usual natural logarithm of the absolute value of x. And then the nth power map corresponds, after passing to heights, to multiplying real numbers by n. So in other words, this multi-radial algorithm, what this is saying is that this theta pilot is such that up to a mild error term, it can't be distinguished from, so the height of the, so the theta pilot corresponds to a certain arithmetic line bundle. The height cannot be distinguished from itself after multiplication by n. So if it literally is invariant with respect to multiplication by n, that would imply that the height is 0. So it's unaffected by multiplication by n up to a mild error term. So this means that there's a bound on the height. So so in the case of IUT, the multi-radial representation for the theta pilot is obtained by means of a sort of analytic continuation along a certain infinite h of what is called the log theta lattice. So this is a lattice given by, so one has at each, so for each pair of integers n and m, one has this bullet, which is a Hodge theater. So it's some sort of model, abstract model of the ring structure surrounding ring structures and scheme structures surrounding an elliptic curve. Then so these arrows do not correspond to morphisms, rather they correspond to gluings between certain portions of the Hodge theaters on either side. So the theta link corresponds, roughly speaking, to the nth power map discussed above, whereas the log link at non-Archimedean valuations looks like the p-adic logarithm. And So the point is that one wants to show that the ring structure is here, the ring structure is on the left-hand side of the theta link and right-hand side of the theta link. Certain portions of the ring structures cannot be distinguished from one another. And so one would, in some sense, like to be able to switch the left and right-hand sides of the theta link. And so a priori, again, the nth power map is not symmetric. So if you raise p to the nth power, that's not the same as taking the nth root of a prime number p. So it's very far from being symmetric. So it's remarkable in some sense. It's sort of a miracle that up to mild indeterminacies, one can obtain such symmetry properties. And so such symmetry properties are obtained by various descent operations involved. So first one descends along this column to obtain objects that are invariant with respect to the log link. And that's the first step. And then one descends further to the extent that one really obtains objects. So this is the multi-radial representation, which is has this symmetry property that you can't tell whether you started from the left-hand side or the right-hand side. And so the main step is really this first step that involves, so each of these steps involves introducing various indeterminacies and showing that the data that one is interested, if one introduces those indeterminacies, is in fact can be reconstructed from weaker and weaker input data. So the main step is this, again, this first step, and this is obtained by constructing invariants with respect to the log link. So in other words, essentially invariance with respect to the logarithm, p-adic logarithm, which has the effect of juggling addition and multiplication. So just as in the case of classical complex Teichmu theory, in some sense one has two underlying dimensions of a ring. So that you can think of those underlying dimensions as being addition and multiplication, or in the case of local fields as units and value groups. And so the nth power map basically dilates the value groups and does not dilate the unit groups. So obtaining invariance with respect to addition and multiplication, or p-adically locally with respect to a juggling of units and value groups, means that the structures that are dilated are, up to perhaps some mild indeterminacies, essentially non-dilated. So this affects a sort of miraculous rotation from the theta link to the log link, which, so it's a rotation from the mysterious log volume dilating theta link gap, the gap between these ring structures and these ring structures. So in other words, the gap between the output of raising to the nth power and the input of raising to the nth power. So that is what is mysterious. And so the multi-radial representation has the effect, in other words, taking invariance with respect to the log link has the effect of translating, of rotating this mysterious gap into a harmless log volume preserving gap. So the logarithm, p-adic logarithm, preserves log volume. So the log volume is just the log of the natural log of the real number given by the volume, the positive real number given by the volume. So anyway, so the point is that I want to go through all these aspects of IUT briefly because they correspond to two interesting aspects of the theory of GT. So so next I want to discuss a technical lemma, which is fundamental to the theory that concerns GT and mapping class groups, profinite mapping class groups, or profinite completions of mapping class groups. So this is the theory which is currently work in progress, which I refer to as CAT, combinatorial algebraization theory. And so the following lemma is a very elementary result in what I call combinatorial function theory that concerns idempotence. So one starts with a perfect field K, an affine hyperbolic curve X over K, an infinite set of points over an algebraic closure of K. So this is not written explicitly, but this is an algebraic closure. K bar is an algebraic closure of K. Y is a finite tau Galois covering of X over K, whose Galois group we denote by Q. So then by evaluating functions of on Y at these active points of Y. So these are this is the inverse image in Y in YK bar of the subset of XK bar given by these active points of X. So we obtain an embedding of Ry into this set of set theoretic functions from the active points of Y to K bar. And so then Rx is then also embedded as a subring. And so if A is a finite set, then we assume that we're given some collection of subrings R alpha, so which contain Rx, and which are isomorphic to Ry as an Rx algebra, and which are moreover stabilized by the natural action of Q on this function space in such a way that Q, this action induces an isomorphism of Q with the Galois group of R alpha over Rx. So really, so typically one can think of these copies of Ry as obtained by allowing some groups such as the Grothendieck Teichmu group or some profinite completion of a mapping class group to act on Ry. So then we write Ra for the sub-Rx algebra generated by these R alphas. And so one verifies immediately that after possibly removing finitely many elements, we can always remove finitely many elements from X-act, from the set of active points of X, that we may assume, so this is just elementary commutative algebra, that Ra is an Rx flat quotient of this tensor product of the R alphas over Rx, and hence is finite étale over Rx. So in particular, spec Ra has only finitely many connected components. And so we write I for this finite set of connected components of spec Ra, and E for the set of idempotence of Ra corresponding to the elements of I. So there's a natural bijective correspondence between E and I. So this is so now Q acts naturally on all of these objects, Ra, R tensor, and also E and I. And so so one verifies immediately that one might think of E as a set of mutually orthogonal idempotents of Ra of maximal cardinality. And so then the lemma, the assertion is that there exists an infinite subset, exact dagger, of this set of active points of X, such that if we restrict all these objects to y-act dagger, so this is just the inverse image in yk bar of the subset of xk bar given by x-act dagger. So if we restrict all these objects, all these subrings and so on, or subsets, to y-act dagger, then and then we write so E dagger. So in the case of E, some of the idempotents might restrict to 0. So we write E dagger 0 for just the restrictions, and then we take the non-zero elements of E dagger 0 to be this subset E dagger. So then E dagger satisfies the following properties. So the set E dagger is a set of mutually orthogonal idempotents of R dagger A of maximal cardinality. So it's a natural bijective correspondence with the set of connected components of spec R dagger A. And the main point, so this is in some sense the main point of all of this, is that the natural action of Q on E dagger is transitive. So we'll come back to this later in section 4. And also, so on each fiber over a point lowercase x of uppercase x act dagger, so each fiber is a Q torsor. And so when restricted to such a fiber, these idempotents just look like, so the supports of the idempotents just look like various cosets with respect to this subgroup H, which is the stabilizer of any element of E dagger. So the Q conjugacy class of H is independent of the choice of an element of E dagger. So the point is that there exists an infinite subset. There exists an infinite subset that such that this transitivity property is satisfied. And the reason for this is that basically one can consider the Q orbits of E. And so these are mutual orthogonal elements which may be thought of as idempotents of this function space of k bar valued set theoretic functions on X act. And so this just means, if one thinks about what that means, that just means that one has a finite partition of X act. So if one looks at the supports of these idempotents, one gets a finite partition of X act. And so since any finite partition of an infinite set into a finite disjoint union of subsets contains at least one infinite set, that implies the existence of a subset, an infinite subset, such that if one, which is the support of some element in this EQ. So then it's a tautology that once one restricts to this subset, all these properties are satisfied. It's very elementary and easy to verify. So right, so now I want to go on to discussing CAT, combinatorial algebraization theory. So this may be thought of as an application of IUT type techniques. It's not logically dependent on the original version of IUT, but it's an application of IUT type techniques to study the Grothendieck Teichmu group or mapping profinite completions of mapping class groups. And so, again, the point is that in many, many respects, um, it's entirely analogous to complex Teichmu theory and really to IUT. Again, it's not logically dependent on IUT. And so also I should say, just in the context of this other talks at this workshop, so so one of the main messages here is that I think so far when in discussions of IUT, many people have given too much attention to the ABC inequality. And so the point here is that the message is that the ABC inequality is one interesting consequence of IUT, but IUT is really much more than the ABC inequality. It's about all sorts of aspects of Anabian geometry. And so one important aspect is the section conjecture. And so this is what is going to be discussed in, was partly mentioned in Hoshi's first talk and will be discussed further in Hoshi's second talk. So IUT is not just about the ABC inequality. The ABC inequality is sort of a special case of the application. It's a special case of one portion of the application to the section conjecture. So it's really sort of a byproduct, a relatively weak byproduct of the application to the section conjecture. And so anyway, the point is that IUT is not really, you shouldn't think IUT equals the ABC inequality. IUT is about various properties in Anabian geometry that relate to the understanding the relationship between addition and multiplication. And so the section conjecture is one important aspect. Also, I'm not sure to what extent Hoshi will discuss the relationship to certain zeros of certain L functions. So here I want to discuss the relationship of IUT techniques to GT and mapping class groups. So also I guess in the context of Pierre Loschak's talk, Pierre Loschak at the end of his talk mentioned various dichotomies between, for instance, the discrete and the profinite theory, and also between genus 0 and higher genus, and also between the point of view of GT being related to GQ and GT being related to deformations of algebras. So in some sense, all of those aspects, but especially the first two aspects, can already be seen very explicitly here. The discrete case corresponds to complex Teichmu theory, whereas this profinite complex case corresponds to CAT, which I will discuss in present section 4. And then the genus 0 versus higher genus aspect corresponds to this GT versus completions of higher mapping class groups, which also appears in this discussion. And then this aspect of GQ and deformations of algebras. So I'm not actually familiar with this theory of Drinfeld and so on in detail, and I don't think that it's not clear to me that aspect of the analogy is so strong, but it is related in that it's very much so. You could see in section 3 that this aspect of considering various kinds of algebras appears, and also I believe in various. I'm not familiar with this theory, but in various aspects of Drinfeld theory, when considers Q parameters and theta functions. And so that's also very closely related to both the IUT and to CAT. So I'm not so certain. I don't really know the details about this final aspect. But anyway, it's interesting that those various aspects that were referred to at the end of Pierre Loschak's talk can also be seen here. So the starting point of CAT involves considering distinct conjugates of GQ, or the image of this étal fundamental group of the moduli stack of R-pointed hyperbolic curves of genus G over the rationals inside out pi x, where x is a hyperbolic curve over Q bar of type GR in this case, and 0, 3 in the case of GT. So one has various, a priori, various conjugates of GQ inside GT, or of this image inside out pi x. And the point is that one wants to think of the ring theory associated. So I want to especially concentrate on the case of GT. The ring theory associated to this conjugate. So one can think of it as a sigma labeled copy of Q bar and a tau labeled copy of Q bar. And the relationship between those two copies is given by these embeddings of the respective Galois groups into GT. So if there are distinct conjugates inside GT, that's a relationship between this sigma labeled copy of Q bar and the tau labeled copy of Q bar that cannot be described in a ring theoretic way. It's some mysterious non-theoretic, purely combinatorial or group theoretic link between these two copies of Q bar. So if you assume that there is an isomorphism between the sigma labeled copy of Q bar and the tau labeled copy of Q bar, that is, so you have a sigma labeled copy of Q bar and a tau labeled copy of Q bar. If you assume that there is a field isomorphism that's compatible with this these embeddings, that then basically you're assuming that they are in fact the same conjugates. So if you start out with distinct conjugates, then you have to distinguish these two ring structures, and this corresponds precisely to the two distinct holomorphic structures in the complex dilations of complex Teichmu theory discussed in section 1, or alternatively to the nth power map, the theta link discussion in section 2, where you have one ring structure on the input side of the nth power map and a distinct ring structure on the output side of the nth power map. So this corresponds to this is some, one should think of this as some profinite kind of dilation, Teichmu dilation. So in the case of CAT, it turns out that the analysis of idempotence discussed in section 3, so basically one embeds the function field of X into some product over P, over of various function spaces of the sort considered in section 3. So I don't want to discuss these function spaces in detail, but basically, so in the case of GT, one is considering a Zariski dense set of finite primes of Q bar. And in the case of MGR, one is considering a Zariski dense collection of Q bar valued points of MGR that arise from certain Hurwitz schemes. And the point is that this analysis of idempotence in section 3 allows one to achieve a sort of miraculous rotation of the sort that we observed in the case of IUT between the mysterious gap so the mysterious gap constituted by these distinct ring structures. So this is what I was discussing here. Right, so the distinct ring structures associated to sigma and tau, that's mysterious. That's what we don't understand. It yields a miraculous rotation from this mysterious gap into the harmless gap between Q conjugates, where Q is a finite center-free characteristic quotient of this geometric fundamental group pi x. And so this is relatively harmless kind of gap. So this is in some sense what was also discussed in Pierre Loschak's talk. With the main non-trivial sort of substantive issue that one is interested in is reducing these GT or mapping class group type gaps into gaps that concern the fundamental group of the actual curve. And so this is what is this miraculous rotation is what is achieved by this transitivity property in section 3. And right, so this is analogous to the miraculous rotation from the theta link to the log link. And so another important aspect of this situation is that, so another analogous aspect when comparing CAT and IUT is that in IUT, the main step in constructing the multi-radial representation is given by considering invariance, obtaining invariance with respect to the log length. So log length rotates addition and multiplication. So obtaining invariance with respect to this kind of rotation is what gives rise to this miraculous rotation from the theta length to the log length in IUT. And if you think about what was done in section 3, the conjugates, the sigma and tau conjugates of the function fields of the curves, a priori they correspond to distinct connected components. So in other words, the gap between GQ and GT, for instance, can be thought of in terms of distinct connected components. And at the level of ring structures, those distinct connected components are given by direct sums of copies of rings. Whereas in the construction of section 3, we considered essentially tensor products, or so rings generated by so quotients of tensor products of conjugates. So the a priori situations where you're considering direct sums of Galois conjugates, and whereas in the construction of section 3, one is considering tensor products of conjugates. And so this is in fact closely related to the classical notion of the Bay restriction. This relationship with Bay restriction also plays an important role. So again, one wants to somehow show some sort of equivalence between these tensor products of Galois conjugates and direct sums of Galois conjugates. So this is also very similar to the key step in IUT. So one important technical tool in CAT is the use of Chebotarev type results, both over number fields and over function fields over number fields in the case of GT. So GT uses both types of Chebotarev, whereas the MGR case uses the Hilbertian property applied to rational varieties over number fields. And the reason why these results play an important role in CAT is that one wants, again, to compute these tensor product group actions in terms of the direct sum group actions. So multiplicative objects in terms of additive objects. So the additive objects are the usual scheme theoretic objects. And the point is that one can only really compute the relationship at these points, fractor P, appearing in this direct product. And so this is why one has to consider decomposition groups of the sort that have nice properties that arise from Chebotarev type results or the Hilbertian property. So these results play an important technical role. I think that this will be discussed in more detail in perhaps not so much detail, but a little bit more detail in Sujirana's talk. And also, another important technical tool is combinatorial and abelian geometry, which will be discussed, so especially this paper CBGT, combinatorial GT, will be discussed in Minamie's talk. And so these are basically natural isomorphisms between the fiber subgroup preserving outer automorphisms, other morphism groups of configuration spaces groups associated to X. So these are the geometric fundamental groups of the nth or n plus one configuration spaces associated to X. So these are the direct products, the complements of the diagonals inside the direct product of n copies of X. And if you think about this passage from xn to xn plus 1, so this corresponds at a node, which may be thought of as a sort of toral or multiplicative kind of object, to a passage to a tripod, which involves additive symmetries. So in some sense involves both the additive and multiplicative structures. And so this may be thought of as a sort of combinatorial analog of the p-adic logarithm, and hence is reminiscent of the log links that appear in IUT. So this kind of isomorphism, which arises from combinatorial and abelian geometry, plays an important role in CAT. It's reminiscent of the role played by log links in absolute p-adic and abelian geometry in IUT. So another important technique in CAT, especially in the case of GT, is the technique of cyclotomic combinatorial Bailey customization. So this is basically diagrams of this sort, where you consider the nth power map on the projective line, and that can be thought of as a covering of the tripod. But then by getting rid of some of the cusps, one can also embed it into the tripod. So incidentally, this was mentioned briefly in Pierre Loschak's talks. I referred to these copies of the projective line minus 3 points as tripods. I think he said something like trignon. I've never heard this word before. Maybe it's something in French. But anyway, I don't use that word. I use the word tripod. But anyway, so these may be thought as analogous to the diagrams that occur in the case of elliptic cuspalizations, which are closely related to the theory of the étal theta function, which plays an important role in IUT. So just to summarize, there are all these analogous aspects. So one starts with, so in the case of complex Teichmu theory, one starts with distinct holomorphic structures on the same underlying topological surface. So this corresponds in IUT to distinct ring structures on the input side of the nth power map and the output side of the nth power map. And so in the case of CAT, one is considering the ring structures associated to distinct conjugates of GQ or the étal fundamental group of the moduli stack inside GT or out pi x. And then the point of the theory is to, in the complex case, to embed these distinct holomorphic structures into a common container, which is a domain. And so again, this domain aspect is very important because it means that you're working with functions that are very close to being, substantially close to being holomorphic. And working with domains is again very important in CAT because one is interested really in seeing what happens, seeing how many connected components you get. And saying, for instance, that you just get one connected component is precisely looking at idempotence, is looking at the connected components and saying that one only has one connected component corresponds precisely to being a domain. So this is very closely related to CAT. So in the case of IUT, one has the multi-radial representation, which allows one to obtain a common container up to mild indeterminacies for distinct ring structures via this miraculous rotation from the theta link to the mysterious theta link gap to the non-mysterious log link gap via rotation of multiplication and addition, and this uses absolute p-adic and abelian geometry, which gives rise to the main indeterminacy of IUT, which is in 3, and also the étal theta function and elliptic actualization. So this is very closely related to, or very closely analogous to the embedding of distinct ring structures in in CAT into this function space via analysis of idempotence and also Chabotarov type results and Hilbertian type results, which yields a miraculous rotation from GT or alpha X conjugates to Q conjugates via rotation of the multiplicative and additive structures. And the main, so other important technical tools include combinatorial and abelian geometry and subatomic arithmetic Bailey hospitalizations. So this is summarized in this illustration. This is IUT and CAT, and so in the case of IUT, one has these log links which rotate multiple structures to additive structures, and then one has the étal homomorphic structures which arise from absolute p-adic and abelian geometry. And so this is analogous to the situation in CAT where one has these configuration spaces which locally at a node look precisely like blowing up. So a node can be thought of as a sort of multiplicative toral object. Blowing up a node gives you a tripod, P1 minus 3 points, which is involves somehow both multiplicative and additive structures. So this can be thought of as a combinatorial analog of the logarithm, the log link in IUT. And GT may be thought of as a sort of invariant of this kind of transformation going up to a higher dimensional configuration space. And so this gap between the invariant object and these Frobenius-like objects in IUT, these kinds of objects here, this is very important in CAT and also plays the fundamental role in IUT. And again, the theta and elliptic hospitalization aspect of IUT may be thought of as analogous to the cyclotomic combinatorial Bailey hospitalizations that play an important role in CAT and will be discussed in more detail in Suzumura's talk. Okay, thank you. This completes my talk.
Thank you very much. So, are there any questions or